Okay, good morning. So we'll pick up where we left off yesterday. And just to get us into the topic again, let me briefly remind you what we did yesterday. So we were considering the behavior of a system near equilibrium. And we had assumed that we were considering small deviations from the equilibrium configuration of the generalized coordinates, and we call this deviation eta. So we had written down the Lagrange function in terms of these deviations eta, which we could also think of as perturbations relative to this equilibrium configuration. Like this. And by using Lagrange's equations on this function, we found that this was the sort of master equation of motion for the etas. We commented that this is in fact a coupled second-order differential equation because of this sum over J. But although it's coupled, it had the form of a one-dimensional simple harmonic oscillator. So we made ansatz for the solution of these etas. But it should look probably something like this. And although it might seem as if each sort of perturbation eta then would be unrelated to the other etas, which might seem a bit strange since we after all have a coupled differential equation, we saw that all the information about the different interactions would be contained in this omega, this eigenfrequency. And we found the following mathematical condition for determining these eigenfrequencies, namely that the determinant of this matrix, where V is a matrix containing these entries Vij, and T is a matrix considering these entries, would provide us with the possible solutions for omega squared. And we introduced the index alpha to characterize or label these eigenfrequencies. And so we endeavored on a journey where we were going to attempt to find a solution for this ansatz, to find a way to establish what the values of AI would be. And we commented that this procedure that we adapted yesterday would only be valid if all the eigenfrequencies were distinct. And I think the last thing we did was to show that these coefficients, AI, would in general be proportional to the minor or cofactor delta I of this matrix, or delta I alpha, in fact. Like this. And we, strictly speaking, only prove this for a particular case of 3 dimensions, but you can easily extend this proof. So we find ourselves today in a situation where we can write the perturbations from equilibrium eta in the following way, where I also underline that the indices here correspond to the direction along the generalized coordinate I in the mode alpha, because you had different modes that the system could sort of oscillate with. Each of these distinct eigenfrequencies will correspond to a different mode. And so if this is the case, we can write down a completely general solution for our problem. Namely like this. The general solution should be a superposition of all of these allowed solutions for each mode alpha. So if you enter a superposition of all the possible allowed modes arising from the eigenfrequencies into the equation of motion, you will see that this is the most general solution. So we have this. And I'm taking the real part here because this corresponds to the actual displacement. It can't be imaginary. So to put it into words, the most general solution for eta I, the deviation from equilibrium, is a superposition of n, which is the number of eigenfrequencies in the system, n harmonic oscillations that have arbitrary phases and amplitudes but fixed frequencies. So the frequencies are fixed from this condition, but this constant of proportionality is in general complex, as we have seen. So this means that both the amplitude and the phase, because a complex coefficient also gives you, in general, a complex phase, or a phase. And so this has to be determined from the initial conditions in the problem. So let me now write this general solution in the following way. Delta I alpha multiplied with this new function, large theta, that I've defined over there. Now it might seem like I'm actually losing some generality here by writing it in this way, because we have written here that eta should be the real part of this entire sum. And what I've done here is that I've basically taken out delta I alpha outside of the real operation here. Why can I do this? absolutely. Everything here is real. We also saw that these eigenfrequencies have to be real. So I'm just extracting this real coefficient outside. So I've written the solution for eta in terms of a superposition of coefficients multiplied with this function here. So since these are coefficients now, we may regard this as new generalized coordinates. This theta contains sort of the unknowns that we have to determine by the initial conditions. And I'll tell you the reason right away for why it's beneficial to write the solution for eta like this. And the reason is that the equations of motions for this function large theta are not coupled. And in fact, they will look like this. Now this is exactly the 1D harmonic oscillator. There's no coupling. So we have one equation of motion for each eigen, or each mode, each eigenfrequency here. So this is trivial to solve for large theta. These large theta functions are known as the normal coordinates of the system. So they correspond to the system oscillating harmonically with eigenfrequency omega alpha, which is clearly seen from this equation here. So the general deviation is a superposition of all these normal modes. So let's see if we can actually obtain this equation of motion, which would make life a whole lot simpler than considering these coupled second-order differential equations. So let's try to insert now our expression for eta I into the kinetic energy and the potential energy to see if we can find the Lagrangian in terms of these normal coordinates, which allows us to derive this equation of motion. So this is the formula for the kinetic energy. And so far we've just used eta as an imaginary coordinate to sort of simplify the analytical calculations. But when we should actually evaluate what the kinetic energy is, we have to remember to use the real part. And I'm using the real part individually of each eta, not the real part of the product, because the real part of the product will also contain the product of the imaginary part of eta, which will give us a wrong result. Okay. I'm just using the small theta here so I don't have to, it takes shorter time to write it. So that's T. Same thing. So this is what we have to work with. And we see that in principle we have quite similar expressions. The main difference here is that you have to consider the time derivative of theta. Let's start off with the potential energy to see if we can simplify this. If we go back to our original equations, we had the following when we wrote eta in terms of this complex coefficient A. So this is, for instance, the equation we used to find this determinant condition for the eigenfrequencies. So let me be specific here to avoid any confusion about which indices you should sum over or not. So there's a sum over j here, but there's no sum over alpha, even if this is a repeated index. So I'm writing here the summations explicitly. Inserting for A, we obtain this. So I can cancel C alpha on each side, since it's just a constant. So why is this useful? Well, we see that we're now in a position where we can actually exchange the sum of Vij, delta J alpha, for this. So we put in omega alpha squared instead. Oh, I'm sorry, it should be a T. Like this, sorry. So we can now exchange this potential energy matrix element with the eigenfrequency and the kinetic energy matrix element. We can substitute it into here. So I'm allowed to do this because the only terms here that depend on j are Vij and delta j beta. So I can take this sum over j and replace it with this sum over j. So I just have to be careful here that the index here is beta. So I should name this beta. So it should be omega beta squared, which I have here. So what I've managed to do here is to express both the kinetic energy and the potential energy in terms of these kinetic energy matrix elements, Tij, at the cost of introducing also the eigenfrequency. Should be a 1/2 here. So you see then that we have rather similar expressions now for V and T. And in fact, they have one thing that is completely in common, and that is this term here, Tij delta I alpha delta j beta. It occurs in both of these expressions. So it would be very nice if we can somehow simplify this particular term, because it would correspond to a simplification in both the kinetic energy and the potential energy. So again, going back to our original equations, we had this. Very well. Let me now write exactly the same equation again, but for a different index. What could be the purpose of this? Well, the purpose of this will become apparent in just a couple of minutes. To see this, multiply first this equation with a sum over delta I alpha. So we obtain the following. And now keep in mind that these entries here for the potential energy and the kinetic energy matrix, they are symmetric. So we can always exchange the indices J and I. So let me do that. I use the symmetry of Vij and Tij, so I exchange the indices. And in addition to this, I multiply the first equation with the same type of sum, only now over delta J beta. Which leads me to the following result. And now I will subtract one of these equations here from the other one. So let me call this one star, this one cross. Which gives me this equation. So this might seem a bit tedious, but keep in mind that our intention from the beginning here was to say something about this quantity here, to see if it could be simplified in some way. Because if it could be simplified, then we could simplify both the kinetic and the potential energy. So I've managed to find the following expression. This coefficient multiplied with precisely the quantity we would like to simplify is equal to 0. So there is one possible solution to this equation, and that is that this quantity is 0. Namely, if omega alpha is not equal to omega beta. So in other words, if the eigenfrequencies are distinct for any alpha and beta, then this expression has to be 0 for any alpha and beta. That's the only way to satisfy this equation. That's a simplification, I would say. It's equal to 0. However, this is only the case if omega alpha is distinct from omega beta. This was one of our main assumptions in deriving all of these results, so it should be valid for our approach. However, if alpha is equal to beta, then we see that this prefactor depending on the eigenfrequencies becomes 0, in which case this factor may be non-zero. So this quantity, to summarize, is 0 if alpha is equal to beta, but it's non-zero if alpha is equal to beta. Did I say that right? Yeah. Do we know any function which has this property, more or less? Being 0 for different indices, but non-zero for equal indices. The Kronecker delta. So we could almost set this equal to the Kronecker delta with only one caveat, and that is that we can't say at this point that it's equal to 1. So this seems like some sort of scaled version of the Kronecker delta. It's non-zero, but we don't know which value. However, I'll present you an argument for why we can in fact set this to be 1. So delta I alpha was defined as the minor I alpha of the following determinant. So since we originally set delta alpha to be the minor of this matrix, it should be unambiguously defined. It has a value, period. However, let's now modify this statement slightly and say that delta I alpha is proportional to the minor of this matrix. Okay, so that may seem a bit fishy. Modifying the statement after I've derived the result, which actually depends on delta I alpha being the minor of this matrix. So how can I salvage the situation? Well, so this is the punchline. We use that this coefficient AI alpha that determined this eta coordinate was proportional to the minor of the matrix by this coefficient C alpha. So let me then write this A coefficient in terms of a new complex coefficient C alpha, multiply with delta I alpha, where delta I alpha is now proportional to the minor. So I'm basically absorbing the proportionality constant from delta I alpha to the cofactor into this new coefficient. You see how I mean? And we see that this coefficient doesn't enter this expression at all. So I should be allowed to do this. I'm basically just choosing new proportionality coefficients so that delta I alpha is now only proportional to the cofactor. And by doing so, the entire derivation that we've done so far is still valid. Any objections to this?
How can the sum then can't we then give the sum any value we please?
Yeah, exactly. That's the point. So by saying, that's the whole purpose of this, that by saying that delta I alpha is now proportional to the minor, we now have an extra degree of freedom in choosing the value of delta I alpha, as you say. Was that your point? Yeah. So whereas before delta I alpha had a fixed value, we now have coefficient of proportionality to play around with, and we can choose this coefficient in any way we like to set this sum to a fixed value. And guess which value we'd like? 1. So we have then managed to simplify this sum to a very neat coefficient, the Kronecker delta. So by doing so, we should be able to considerably simplify the expressions for the kinetic and the potential energy. So this part of the kinetic energy is simply the Kronecker delta in alpha and beta. And so the kinetic energy takes the following form. It's simply the square, the sum over all modes of the square of the time derivative of the normalized coordinate, normal mode. Similarly, we get the following for the potential energy, where I've just now immediately substituted delta alpha beta for this sum here. We see that it takes the following form. And from this, it's not a far step to go to the desired equations of motion, and we'll do this after the break.